Good morning, everyone. My name is Anton Vasiliuk. I am a computer vision researcher and developer. I work at the Artificial Intelligence Research Institute in the group of medical imaging. Currently, I am finishing my PhD degree at the Moscow Institute of Physics and Technology. My research interests lie in reliable machine learning, including auto-distribution detection, anomaly detection, and model robustness. Our group is planning to develop an anomaly segmentation challenge in the following year, and we are open for collaborations. And today, I'm presenting our paper, Redesigning auto-distribution detection on three-dimensional medical images. The structure of my presentation is going to be the following. Firstly, I'll define the standard auto-distribution problem and describe its issues when applied to image segmentation. Next, I'll present our performance auto-distribution framework, including a novel metric. And finally, I'll give some experimental results and practical advantages. So, let's get started. Auto-distribution problem assumes there exists a joint distribution over images and labels, even though we don't know it. However, we are given a set of training samples that we call in-distribution data. Our goal is to develop a classifier of whether the label of a novel sample is the same as in the training distribution. We evaluate this classifier against some data that we call auto-distribution data, with the goal of ensuring generalized reliability. However, the first problem of this setup, we don't know how dangerous it is to miss certain samples. Many researchers evaluate auto-distribution pipelines on the gradual changes. Such changes include varying age, noise, or even scanning locations can be gradual by nature. High distortions are more important to detect, since they degrade performance the most. The second problem is that the level of distortions for a sample to become auto-distribution is not defined. Classification metrics are usually computed to evaluate the auto-distribution performance. However, not all of them suit the task. Auto-distribution events are assumed to be rare, since frequent events can be dealt with the supervised approaches. However, Shirokikh metric averages over the whole range of thresholds, which are mostly irrelevant for auto-distribution problem, since it's not desired to lose most of the in-distribution data to capture some rare auto-distribution events. The same holds true for another classification metric, area under precision recall curve. But this metric also depends on the unknown ratio between in-distribution and out-distribution data. False positive rate at a given threshold is the only relevant metric. However, it also doesn't represent a different sample impact. There are a couple of areas related to auto-distribution detection, but not of them provides complete methodological coverage. Anomaly detection focuses on a similar problem, when no labels are given. The model robustness aims to provide reliable prediction even on noisy data. However, it doesn't cover sample rejection capability. Selective prediction studies sample rejection as a way to gain ID performance, but it doesn't cover auto-distribution cases. So, we propose to look at the auto-distribution detection from a downstream model performance perspective. To exploit our framework in image segmentation fully, two assumptions had to be made. Firstly, we treat the background class as absence of the labeled diseases. We believe that it represents the actual labeling process, and is better suited than treating the background as healthy tissue. Therefore, we can evaluate model prediction on novel samples, as any prediction should be produced only if the target classes are present. The second assumption is that we treat a sample as auto-distribution only if it degrades the prediction quality. We measure the prediction quality on some test ID dataset. If some data produces different quality, there is a difference from the test set that should be detected. In this way, we can measure the distance between images using any metric in the performance space. To finish our framework, we propose a metric that incorporates those assumptions. It's based on the false positive rate computation, and basically is the performance drop on samples that are predicted as in distribution. To compute it, firstly, we select an out-distribution threshold that preserves 95% of the in-distribution data. Using this threshold, we compute the expected performance on the out-distribution data, as written in the equation. S0 is the average ID quality. S of x and y is the prediction quality on a given sample. For example, it can be the die score. Therefore, a zero EPD, or expected performance drop, can be produced by either rejecting all out-of-distribution samples or giving correct predictions, as it can be observed from the image on the right. The green line represents the area where the expected performance drop is 0. This work is not restricted to any setup in particular. However, we show its advantages using a setup presented in our other work, limitations of out-distribution detection in three-dimensional medical image segmentation. We have two in-distribution problems: lung cancer segmentation and vestibular schwannoma segmentation, and a bunch of out-of-distribution sources, including such sources as population change, scanner change, new locations, and a couple of added synthetic noises. And we also explore the same out-distribution methods without any changes. You can check the implementation details in the original paper. These methods include entropy of the prediction, standard deviation of either ensemble or Monte Carlo predictions, generalized Odin method, and singular value decomposition features. The anomaly detections are the winning solution from the mood competition, and a simple method based on the histogram of image intensities. First of all, we show the problem with the classification metrics using our synthetic setups of varying distortion severity. The value of the expected performance drop typically grows along with the growth of the distortion severity. Therefore, it suggests that detecting the most distorted images is of the biggest importance, as they can harm the most. Contrarily, the highest ROC values are the lowest severity, forcibly moving the focus on the research to them. Table 1 presents the comparison of ROC and expected performance drops of die score across all studied setups. There are two key observations that can be made from this table. Firstly, within our framework, we were able to compute a no OOD score of potential performance loss if no out-distribution method was applied at all. This justifies out-distribution detection in most setups, as it allows to preserve the prediction quality. Secondly, expected performance drops produces a different ranking than our ROC. The most notable example of this difference might be the simple entropy method in the MRI setup. Our ROC displays entropy as the worst method, being on par with a random classifier. However, the expected performance drop metric captures its ability to provide correct predictions in most setups, without rejecting them, giving even better quality than on the test set. Finally, EPD metric provides a wider range of methods for analyzing and solving the problem. If we compare the ranking produced by the expected performance drop of minus the average number of false positive predictions, the second row, to the die score, the first row, we observe a different ranking, which highlights the ensemble ability to reduce false positive predictions. Besides, one can enhance model robustness by appropriate training. When we train our unit model with some heavy augmentations, it leads to reduced number of false positive predictions, even without any auto-distribution pipeline. None of the observations can be deduced from ROC-AUG scores. In conclusion, I would like to point out the pros and cons of the proposed framework. Firstly, it doesn't require to put the exact auto-distribution labels. No need to select the threshold at which the data becomes auto-distribution, or even is it auto-distribution at all. This framework allows us to estimate performance drops on given datasets and to highlight the scenarios that may lead to unreliable predictions. Secondly, it measures the actual performance impact of the auto-distribution or anomaly detection pipeline implementation. As EPD can be measured while applied to any ID metric, it shows the impact in terms of this metric. Further, the metrics are not restricted to the segmentation scores and can be even applied to such metrics as user satisfaction rate. Lastly, it supports a wide range of methods designed to solve the same problem, not only through rejection, but also through robust training, for example. However, the main disadvantage of this approach is that it is limited to detecting samples that degrade the actual performance. While these harmless samples don't interfere with the main goal of an algorithm, it may be an implicit indicator that something else has gone wrong that could be missed. So, that's all. Thank you very much for your attention. Feel free to ask me any questions or write me directly via email.